Dear students, welcome to my 6th class on module 2 Fourier series. So in my previous lecture video we learnt about off-range Fourier series and few problems on off-range Fourier series. So in this video also we'll be discussing few more problems on off-range Fourier series. Example number 3. Find the off-range sine series for f of x is equal to x into pi minus x in 0 less than x less than pi. So first you take the formula of off-range Fourier sine series for the pi interval, that is f of x is equal to summation n from 1 to infinity bn sin nx is the formula, and call it as equation number 1. So now they have given that the function is f of x is equal to x into pi minus x in 0 comma pi. So now our job is to find the value of the Fourier coefficient Bn here. So consider Bn is equal to 2 by pi integral 0 to pi f of x sin nx into dx. So now in the place of f of x I am going to replace x into pi minus x. So what will be getting? So 2 by pi integral 0 to pi x pi minus x square into sin nx dx we got. So now to simplify this integral, I am going to apply the Bernoulli's condition. So treating this x pi minus x square as u and sin nx as v, applying the Bernoulli's condition. So the constant 2 by pi I'll keep as it is. So keeping u term x pi minus x square as it is, integrating sin nx, we got minus cos nx by n. So next is minus sin. So now differentiating x pi minus x square with respect to x. So pi minus 2x, and keeping the minus sign as it is and keeping n also as it is. So solving cos nx will be getting sin nx by n, so it will become minus sin nx by n square plus. So now again same thing, solving this function. So pi will become 0, 2x will become minus 2, and integrating sin nx one more time, we got cos nx by n cube with the limit 0 to pi. So now I am going to apply upper limit, replacing all x terms by pi. So what I will be getting? 2 by pi minus of pi square minus pi square into cos n pi by n plus pi minus 2 pi into sin n pi by n square minus 2 cos n pi by n cube, and here 0 minus 0 into cos 0 by n plus pi minus 0 by sin 0 by n square minus 2 cos 0 by n cube. So as you know that sin n pi is 0, sin 0 also 0. So here these two terms will become 0 because both are same. We can cancel this, so it will become 0. And cos n pi is minus 1 power n, cos 0 is 1. So we got 2 by pi minus 2 by n cube into minus power n plus 2 by n into 1 n cube into 1 we got. So auto simplifying by taking 2 by n cube common factor, we got bn is equal to 4 by pi n cube into 1 minus power n is the required value of bn. So now I am going to replace this bn value in the equation number 1. So we got x into pi minus x is equal to summation n from 1 to infinity 4 by pi n cube 1 minus power n into sin nx is the required off-range Fourier sine series for the given function x into pi minus x. Example number 4. Find the off-range sine series of the function f of x is equal to 1 by 4 minus x for the limit 0 less than x less than 1 by 2 and x minus 3 by 4 for 1 by 2 less than x less than 1. So now take the off-range Fourier sine series in the arbitrary interval 0 comma l. So first write the formula. F of x is equal to, we have summation n from 1 to infinity bn sin n pi by l into x. So and take it as equation number 1. And they have given that f of x is equal to 1 by 4 minus x for 0 less than x less than 1 by 2 and x minus 3 by 4 for 1 by 2 less than x less than 1 by less than 1. So totally here the x ranges from 0 to 1. So it implies that the value of the L will be equal to 1 is the arbitrary interval here. So now our job is to find the value of Bn. So Bn will be equal to what? 2 by L integral 0 to L f of x sin n pi by L x dx. So now in the place of L, replace L is equal to 1. So we got the equation 2 by 1 integral 0 to 1 f of x sin n pi by 1 x dx. So now the function I am going to replace with the following limit. So we got 2 into integral 0 to 1 by 2 1 by 4 minus x into sin n pi x dx plus integral 1 by 2 to 1 x minus 3 by 4 into sin n pi x into dx. So now applying the Bernoulli's conditions here. So taking this one as u and this one as v here, and taking this one as u and this one as v here. So after simplification we got 2 into 1 by 4 minus x into minus of cos n pi x by n pi minus 0 minus 1 into minus sin n pi x by n square pi square, the limit 0 to 1 by 2. Similarly solving this function, so x into x minus 3 by 4 into minus cos n pi x by n pi minus 1 minus 0 into minus sin n pi x by n square pi square with the limit 1 by 2 to 1. So now after applying the limit for the first function, we got 2 into um, 2 into minus of 1 by 4 minus 1 by 2 into cos n pi and n pi by 2 by n pi minus sin n pi by 2 by n square pi square, and lower limit minus 1 by 4 minus 0 into cos 0 by n pi minus sin 0 by n square pi square. Next function, so applying upper limit, so 1 minus 3 by 4 into cos n pi by n pi plus sin n pi by n square pi square, and lower limit minus 1 by 2 minus 3 by 4 into cos n pi by 2 by n pi plus sin n pi by 2 by n square pi square. So as you know that sin n pi is 0, sin 0 also 0. So after simplifying this, we got the equation like 2 into 1 by 4 cos n pi by 2 by n pi minus sin n pi by 2 by n square pi square plus 1 by 4 cos 0 by n pi minus 1 by 4 cos n pi by n pi minus 1 by 4 cos n pi by 2 by n pi minus sin n pi by 2 by n square pi square. So after simplifying this, we can cancel these two, and we got the value like 2 times of 1 by 4 n pi into 1 minus 1 by 4 n pi into minus 1 power n minus 2 times of n square pi square into sin n pi by 2. So finally we got Bn is equal to 2 times of 1 by 4 n pi into 1 minus power n minus 4 by n square pi square into sin n pi by 2. So therefore the value of Bn will be equal to 1 by 2 n pi into 1 minus power n minus 4 by n square pi square into sin n pi by 2 is the required value of Bn. So now I'll be incorporating this Bn value in the equation number 1. So we got f of x is equal to summation n from 1 to infinity 1 by 2 n pi 1 minus power n minus 4 by n square pi square sin n pi by 2 into sin pi x is the required off-range Fourier sine series for the given function f of x. Okay, in the next lecture video, we'll be discussing the new concept, that is practical harmonic analysis. Thank you.